A fisherman was 62 miles out to sea, open ocean, no land, no storm, and the water in front of him started to boil. Then came the smell, hot metal, sulfur rising from the deep. Then a column of black ash shot through 1,600 feet of ocean and burst into the sky. This volcano had been silent for 54 years. Nobody alive had ever seen it erupt, and on May 8, 2026, it woke up. We'll go inside the crater forming right now on the ocean floor, revisit a tsunami that erased villages in 1888, and ask whether our warning systems can even see what's coming. If this keeps you up at night, like and subscribe. More is coming. Let's go. Kennedy Massis was looking for tuna. That was the whole plan. Head out into the Bismarck Sea, find the fish, come back. Simple. He had done it hundreds of times before. The ocean that morning looked the same as always. Deep blue, flat horizon, nothing unusual in any direction. Then the smell hit him. Hot metal, sharp and chemical, like the inside of a machine that had been running too long, mixed with something heavier underneath it. Sulfur, the kind of smell that coats the back of your throat and stays there. Kennedy had spent years on these waters. He knew every kind of smell the ocean makes. This was none of them. He looked around. No other boats, no smoke on the horizon, no storm clouds building anywhere, just open water, and this smell rising up from below like the sea itself was on fire. He was 62 miles from the nearest land. That is roughly the distance from downtown Los Angeles to the edge of the Mojave Desert. 62 miles of deep ocean, and something beneath it was producing a smell strong enough to reach the surface air and fill his lungs. That smell has a name in geology. Scientists call it volcanic outgassing. Here is what it actually means. Deep underground, magma carries dissolved gases trapped inside it the same way a sealed soda bottle carries carbon dioxide. When the pressure holding those gases in place drops suddenly, they release. Fast. The gases shoot upward through cracks in the rock, through miles of ocean water, and into the air above. The two biggest ones are sulfur dioxide and hydrogen sulfide. Sulfur dioxide smells like a struck match. Hydrogen sulfide smells like rotten eggs mixed with rust. Together, rising from a fresh volcanic vent, they produce exactly what Kennedy described: hot metal, sharp, chemical. Wrong. The fact that Kennedy could smell it at all was a signal, a serious one. For volcanic gases to reach the surface with enough concentration to be noticeable, the vent producing them has to be releasing a massive volume. A slow seep through the seafloor gets diluted across miles of cold water before it reaches the surface. Kennedy's nose was essentially detecting the exhaust of an eruption powerful enough to force gases up through more than 1,000 feet of ocean without losing their punch. He had no idea yet what was actually happening beneath him. Underneath his boat, the seafloor was breaking apart. A fissure ridge running 3 miles across the ocean floor was cracking open along fault lines that had been locked and frozen since 1972. Magma from deep inside the earth was pushing upward through those cracks, heating the water around it to extreme temperatures and releasing enormous quantities of gas in the process. Kennedy did not have a seismometer. He did not have satellite data. He had his nose, and his nose was telling him something was deeply wrong. He started scanning the water ahead of him. That is when he saw it, a section of ocean that looked different. The surface was moving in a way the waves around it were not, churning from below, rising and breaking in tight, fast circles. White foam spreading outward from a central point. The water was not calm. The water was not normal. The water looked like the surface of a pot left on a stove too long. He had found the eruption. Except he did not know that yet. What he was seeing had a scientific explanation, and understanding that explanation changes how you see everything that happened next. Most people picture the ocean floor as flat, calm, and frozen in place. The Bismarck Sea's floor is none of those things. Underneath the water north of Papua New Guinea, the ground moves constantly. The plates beneath the Bismarck Sea are called microplates. Think of the Earth's outer shell like a cracked eggshell floating on a slow river of melted rock. Most of the major pieces of that shell are enormous. The Pacific Plate alone covers an area bigger than all of Asia, but in certain zones, the cracked shell has fractured into much smaller pieces, faster ones. The Bismarck Sea sits directly on top of one of the most complex collections of these fast-moving microplates on Earth. Scientists confirmed this. The South Bismarck Plate and the North Bismarck Plate are being pulled in different directions at the same time, grinding and colliding along fault lines that run directly beneath the seafloor in this region. Smaller plates move faster. That is a confirmed rule in geology. A plate the size of a state moves with more speed and less stability than a plate the size of a continent. And faster movement means more friction. More friction means more heat. More heat means more melted rock building up in underground chambers. More melted rock building up means pressure. Relentless, mounting pressure with nowhere to go except upward. The Bismarck Sea is sitting on top of a pressure system that has been building for millions of years. There is also something called a subduction zone operating in this region. One plate is being pushed underneath another. As it sinks, the rock melts. That melted rock rises. It collects in magma chambers beneath the sea floor. When the chamber fills past its limit, it finds a weak point in the crust above it and forces its way through. That weak point, in this case, was a fissure ridge running along the central Bismarck Sea floor. A ridge that first cracked open in January 1972, a ridge that scientists lost track of for 54 years. Here is the detail that should make you pause. The Bismarck Sea has produced some of the largest and most violent tectonic events ever recorded in the Pacific region. Earthquakes above magnitude 7 are common in this zone. Confirmed. Volcanic activity along the seafloor is ongoing in multiple locations, simultaneously. Confirmed. The fault lines running through this area have triggered some of the most destructive waves in Pacific history. We will get to one of those later, and it is worse than you expect. The region is also poorly mapped. Scientists have detailed charts of Mars's surface, but the floor of the Bismarck Sea remains largely unexplored. Large sections of the seafloor here have never been seen by human eyes or robot cameras. The exact layout of the fault lines feeding the volcano Kennedy Massis stumbled onto is still an unknown. A system this unstable, this active, and this poorly understood, sitting beneath an ocean used daily by fishing communities, was always going to produce a moment like May 8, 2026. The earthquake that triggered this eruption was not random. It was the result of pressure that had been building in a closed system for decades, a locked fault snapping under strain it could no longer carry. And what that snap set in motion underground was far bigger than the 7-second rumble fishermen felt in their hulls. The machinery that woke up that morning had been silent since before most of the people reading the warning reports were born. Nobody saw it happen. January 1972. The central Bismarck Sea. A volcanic eruption somewhere on the deep ocean floor. No ships were nearby, no cameras, no one watching from shore, because the eruption site was more than 60 miles from the nearest coastline. The ocean surface gave nothing away. From above, it looked like water. But something was listening. During the Cold War, the United States military built a network of underwater microphones across the ocean floors of the world. The system was designed to track Soviet submarines. The microphones were extraordinarily sensitive. They could pick up the sound of a propeller turning miles away, track the low hum of an engine running at depth, and detect pressure waves moving through deep water that no human ear could ever register. When the central Bismarck Sea volcano erupted in January 1972, those sensors heard it. The confirmed record shows that acoustic monitoring stations picked up explosive signals originating from the ocean floor north of Papua New Guinea. The signals matched the acoustic profile of known submarine volcanic events. Scientists analyzing the data traced the source to a deep fissure ridge. That was the first confirmed detection of this volcano's existence. Think about what that means. The volcano had existed for millions of years. Humans had sailed across the Bismarck Sea for centuries. Fishermen, traders, explorers. Nobody knew what was directly beneath them, because the ocean floor in that region was invisible, and the volcano had simply never erupted hard enough at the surface to leave any sign. It took a Cold War surveillance system, built to track weapons, to accidentally discover a geological structure the size of a small mountain range sitting on the ocean floor. The acoustic signal that gave the volcano away travels through water at roughly 1 mile per second. That is 4 times faster than sound moves through air. Deep ocean water acts like a highway for pressure waves. A single volcanic explosion can send a signal thousands of miles across an ocean basin, arriving at a monitoring station with enough clarity to be identified and located. Scientists can triangulate the source using the time difference between when each sensor in the network picks up the signal. In 1972, the signals confirmed an active vent. The eruption was brief, then it stopped. The volcano went quiet. Scientists logged the location, assigned it a number in the Smithsonian Institution's Global Volcanism Program catalog, volcano number 250,030, a confirmed entry. A real structure, a documented eruption history going back exactly one event. Then the monitoring stopped. The volcano was dormant. Resources moved elsewhere. Over the following decades, as funding shifted and the Cold War wound down, active surveillance of that specific ridge faded completely. The volcano dropped off monitoring rosters. 54 years passed. Think about how long that is. A person born the year that volcano last erupted would be in their early 50s today. An entire generation grew up, went to school, had careers, and nobody was actively watching that ridge. The sensors existed, but the data coming from that location was quiet. Scientists were not checking for this particular site's return. The volcano had gone from discovered to forgotten in the span of a few decades, and when something that has been asleep that long finally decides to wake up, the first sign does not come from a satellite or a scientist. It comes from a crack in the rock, a shift in the pressure, and a chain of events underground that takes time to reach the surface. The first modern warning came from the ground itself. Close your eyes for a second and imagine the loudest sound you have ever heard. A jet engine, a thunderclap directly overhead, a fireworks explosion at close range. Now multiply that. A volcanic eruption on the ocean floor produces pressure waves that dwarf almost any sound a human has ever experienced, directly, and the ocean carries those waves across distances that would make the sound fade to silence on land. Kennedy Massis described the sound of the eruption as heavy thunder. That comparison is useful, but incomplete. What he was hearing was the surface echo of explosions happening deep underwater. By the time the sound reached open air, it had already lost most of its force fighting through hundreds of feet of ocean. The original source was louder by an enormous degree. Here is why water changes everything. Sound is a pressure wave. It is a series of compressions moving through a material. The denser the material, the faster sound moves through it, and the less energy it loses over distance. Air is not dense. Sound in air fades quickly. The atmosphere scatters and absorbs pressure waves within miles. A massive explosion on land might be heard 30 or 40 miles away. Past that, silence. Water is about 800 times denser than air. A pressure wave moving through ocean water loses a fraction of the energy it would lose in air over the same distance. A deep underwater explosion does not just make noise in its immediate surroundings. It sends pressure waves traveling across entire ocean basins. The acoustic monitoring network built in the Cold War, the one that first detected this volcano in 1972, was designed around exactly this property. Sensors positioned thousands of miles apart could detect the same event, because water carried the signal that far. The specific depth where pressure waves travel with the least energy loss is called the sound fixing and ranging channel. Scientists confirmed its existence decades ago. It sits at roughly 3,000 feet in most ocean basins. Volcanic explosions that happen near or below this depth inject their pressure waves directly into this highway, and the sound can travel tens of thousands of miles before fading. The central Bismarck Sea eruption in 2026 produced explosions at a vent somewhere between 1,600 and 4,000 feet deep. That places the source at or near the depth where ocean acoustics are most efficient. The sound Kennedy heard from his boat was the leakage, the fraction of the acoustic energy that escaped upward through the water column and broke into air. He compared it to thunder. Scientists monitoring the event from acoustic stations across the Western Pacific were receiving something far more detailed, the full signature of a volcanic explosion, the exact frequency profile, the rhythm of the blasts, the intervals between them. From that acoustic data, trained analysts can estimate the size of the explosions, the volume of material being released, and whether the eruption is accelerating or slowing down. Kennedy had no instruments. He had his ears and his experience on the water. He knew a storm sound from a deep sound, and what he was hearing came from below. That distinction matters, because the next thing he saw confirmed what his ears were already telling him. Here is a question worth sitting with. How do you lose a volcano? The answer is simpler and more unsettling than it sounds. You stop looking for it. After the 1972 detection, the central Bismarck Sea volcano had one confirmed eruption on record and zero activity since. Dormant volcanic structures are everywhere on Earth. There are estimated to be more than 1 million volcanic features on the ocean floor, and the vast majority of them are inactive. Scientists cannot actively monitor all of them simultaneously. Resources go towards structures that show signs of life. This one showed none. Decades passed. The Global Volcanism Monitoring System tracked active volcanoes on land with ground sensors, satellites, and regular reporting networks. Submarine volcanoes are far harder to monitor. You cannot place a ground sensor on an ocean floor 2,000 feet down without a dedicated deep-sea operation. Satellites can detect heat signatures and ash plumes once they reach the surface, but a volcano venting slowly at depth produces no surface signal at all. The central Bismarck Sea structure simply stopped producing signals. No acoustic bursts, no seismic tremors linked to the site, no surface disturbance, nothing to flag a monitoring system. The volcano was listed in the Smithsonian catalogue, given its confirmed history, and left as a dormant entry. There is a deeper issue embedded in this. The ocean floor is the least explored surface on Earth. Scientists have mapped more of the moon's surface in detail than they have mapped the bottom of the ocean. The technology required to survey deep seafloor terrain is expensive, slow, and limited in coverage. Research vessels are few, deployment windows are short. Priority goes to regions with confirmed recent activity or high population exposure. The central Bismarck Sea, deep and remote, ranked low on that priority list. When magma systems go dormant, they do not disappear. The underground chamber does not drain. The fault lines do not heal. The geological pressure that created the volcano in the first place does not go away. It pauses, the system cools slightly at the margins. The crust above it locks back down, but the heat source feeding it from below, the slow convection of the Earth's mantle, keeps operating on its own timeline, completely independent of any human monitoring schedule. 54 years of silence means 54 years of pressure building in a closed system with no release. Magma accumulating, gas dissolving into that magma under increasing pressure. The chamber ceiling holding, until it did not. Scientists knew, in theory, that this was possible. Any dormant submarine volcano with a confirmed eruption history carries the potential for reactivation. The timing is simply impossible to predict. A structure might sleep for 100 years or 500, Some go dormant for thousands of years and then return. The geologic clock runs on a scale that makes human monitoring schedules look like a blink. The volcano spent 54 years building toward May 8, 2026. And when the ground finally moved that morning, the first signal came from below the seafloor, not from any human watching station. That signal was the earthquake. And understanding exactly what that earthquake did underground explains everything that followed at the surface. The first sign was not an ash plume. The first sign was the ground moving. At some point on the morning of May 8, 2026, the crust beneath the central Bismarck Sea reached its breaking point. The fault lines locked across that ridge for over 5 decades released. The energy stored in that locked zone discharged in seconds. Seismometers across Papua New Guinea and across the broader Western Pacific network registered the event simultaneously. The Mineral Resources Authority of Papua New Guinea assigned it a confirmed magnitude of 5.4. That is the official number from the official monitoring body for this region, and it is the most trusted measurement available. Independent analysts looking at the same seismic wave data came up with 5.6. Both numbers are confirmed readings from different instruments with different calibrations. The difference between them is small, but at the scale of a geological rupture, even a small difference in magnitude represents a significant difference in the energy released. A magnitude 5.4 earthquake releases roughly the same energy as a small nuclear device. The ground across the seafloor of the Bismarck Sea snapped. Rock that had been locked under pressure for 54 years suddenly moved. The displacement happened fast, measured in seconds, and the shockwave radiated outward through the crust, in every direction. People on nearby islands felt it. Boats on the water felt it. Buildings in coastal communities of Papua New Guinea registered it through their foundations. But the event that mattered most happened underground, where no one could see it. The fault rupture did not just shake the seafloor. It fractured the ceiling of a magma chamber that had been sealed and pressurized for decades. Think of pressing your thumb down on the top of a full can that has been shaken. The pressure inside is already at maximum. The moment the structural resistance at the top gives way, everything inside forces outward. The magma chamber beneath the central Bismarck Sea ridge did exactly that. The moment the fault cracked open, it created a pathway. Molten rock under enormous pressure found the gap and moved upward. Not slowly. The pressure differential between a sealed magma chamber and open ocean water is extreme. The magma, loaded with dissolved gases, began racing upward through the fissure. Within hours of the main earthquake, the ocean surface above the site began showing signs. The water changed first. Temperature sensors in the area, read through satellite thermal imaging, picked up a warm patch forming on the surface. Then the color shifted. Volcanic material mixing with ocean water produces a distinctive discoloration, a murky greenish-gray spreading outward from a central point. Then the gases arrived. Sulfur dioxide and hydrogen sulfide, the same gases Kennedy Massis would smell the following day, broke the surface first. Invisible, but detectable by the change in smell. Then the ash came. The first ash plume broke the ocean surface confirmed on May 9, 2026. One day after the earthquake, it took that long for the material from the vent to fight through 1,600 to 4,000 feet of ocean water and reach open air. When it arrived violently. Most earthquakes end at the earthquake. The ground shakes. Buildings crack, people run outside, then it stops. The damage is physical, immediate, visible. After a few days, the story moves on. For the vast majority of earthquakes that happen every year across the Pacific, that is the complete sequence. But certain earthquakes do something different. They do not just release energy, they rearrange the plumbing. The crust beneath the ocean is not a solid sheet of uniform rock. It is layered, fractured, and full of channels. Some of those channels carry water, some carry gas, some carry magma. The rock around them acts as a seal, keeping the material under pressure inside its container, the way a pipe carries water without leaking as long as its walls hold. A fault rupture is a sudden, violent reorganization of the rock along a crack. The two sides of the fault shift. Sometimes one side drops. Sometimes they slide past each other. In every case, the movement is abrupt and massive. The displacement can be measured in feet, happening in a time frame measured in seconds. When that displacement happens directly above or adjacent to a sealed magma chamber, it does something specific. It changes the pressure balance. A magma chamber has a ceiling of solid rock between its contents and the ocean floor above. That ceiling is under two opposing forces. The magma below pushes upward with extreme pressure. The weight of the ocean floor rock above pushes downward. As long as those forces are balanced, the chamber stays sealed. The magma stays underground. The fault rupture on May 8th broke that balance. When the crust along the ridge fractured, the structural integrity of the ceiling above the chamber dropped. The rock cracked. The downward force holding the magma in place decreased locally along the fracture lines. The magma, still pushing upward at the same pressure, suddenly had less resistance to push against. The pathway opened. This process has a scientific name: volcanic triggering by earthquake. Scientists have confirmed it in multiple locations globally. The most famous documented case is Mount Pinatubo in the Philippines, where a magnitude 5.9 earthquake in 1991 preceded its catastrophic eruption by 2 months. In that case, the earthquake cracked open sealed gas pockets in the volcanic system, rapidly increasing the internal pressure and accelerating the magma's rise. At the Bismarck Sea Ridge, the process appears to have been faster. Within hours of the magnitude 5.4 event, the vent was already producing output at the surface. That speed suggests the magma was already close to the ceiling before the earthquake, the chamber already under high pressure, already near the threshold where it needed only a small structural change to break through. 54 years of pressure building, one fault rupture, hours to the surface. The earthquake did not create the eruption. The eruption was already waiting. The earthquake simply removed the last obstacle between the magma and the open ocean above it. Understanding this changes the question scientists are now asking. The question is no longer whether the volcano is active. It demonstrably is. The question is how much material is in that chamber and whether the eruption has relieved the pressure or barely scratched it. That answer could determine whether what Kennedy Massis saw on May 9th was the peak of this event or just its opening moment. Kennedy Massis was not supposed to be a witness to history. He was looking for tuna. That was his job, his income, the reason he was 62 miles out into the Bismarck Sea on the morning of May the 9th, 2026. He was scanning the water the way commercial fishermen scan it, reading the surface, looking for signs of where the fish are running deep below. And then the ocean in front of him started behaving in a way it had no business behaving. The surface was churning in a tight circle, white foam spreading outward from a central point, like something enormous was forcing its way upward from below. The waves around that section were moving normally, driven by the wind and the surface current, but inside that circle the water was moving against all of that, rising, churning, breaking in short, violent bursts that had nothing to do with any weather above. Kennedy described it as the reef boiling. That image is accurate in a physical sense. The water above the vent was receiving enormous heat from the magma and volcanic material rising through the fissure below. The temperature differential between the superheated water at the surface of the vent and the surrounding ocean was extreme enough to produce rapid convection. The water was cycling upward from below at high speed, just like water in a pot, cycling upward when the burner underneath it runs hot. Except the burner in this case was a geological event happening more than 1,000 feet below him. Then came the smoke, dark columns rising directly out of the water. Kennedy looked at the horizon and saw no storm. The sky above him was clear in the directions weather comes from. but the smoke was rising from the ocean itself, thick and dark, and it was moving upward fast. He described the sound at this point as heavy thunder, a deep, rolling boom that he felt more in his body than he heard with his ears. Then another, rhythmic and heavy, coming from below. He had never heard a volcano erupt. He grew up on these waters. He knew thunder. He knew the sound of an engine failing on a boat. He knew the crack of a large wave breaking against a hull. None of those sounds matched what he was hearing. What he was experiencing was the acoustic pulse of underwater explosions reaching the surface and transmitting into open air. Each boom was a burst of volcanic material and gas forcing its way upward through the water column with enough force to break the surface and discharge into the atmosphere. The intervals between the sounds gave the impression of thunder rolling across a distant storm front, except the source was directly below the surface in front of him, not somewhere across the horizon. The air around him carried the metallic sulfur smell he had already noticed. Now it was stronger, dense enough to taste. Kennedy was the first human to make visual, auditory, and sensory contact with the eruption. No scientist, no satellite operator, no government official registered the event before he did. He was a fisherman looking for tuna, 62 miles from shore, and he became the first recorded observer of the first eruption of the Central Bismarck Sea volcano in 54 years. He turned his boat around. What he left behind kept building. The word boiling needs some precision here. When Kennedy described the water as boiling, he was not describing water turning to steam at the surface. Open ocean water cannot boil the way water in a pot does, because the ocean surface is exposed to atmospheric pressure rather than sealed above a contained heat source. What Kennedy was seeing was something different, and in some ways more violent. Volcanic vents release material in multiple forms simultaneously: superheated water, molten rock, dissolved gases, ash and rock fragments. When all of that exits through a fissure on the seafloor, it rises through the water column at speed, driven by pressure and buoyancy. The hot material heats the surrounding water as it rises. That heated water becomes less dense and rises faster. The result is a rapidly cycling column of water moving upward from the vent to the surface, carrying heat, gas bubbles, and suspended particles with it. At the surface, this column breaks through. The water churns, bubbles burst, gas escapes into the air, rock fragments and ash arrive in the mix. The surface becomes discolored, greenish-gray or dark brown, depending on the composition of the material, because volcanic ash and minerals cloud the water with fine suspended particles. The smell of sulfur compounds breaks into open air at the same time the visual disruption appears. All of this happens fast. Eyewitness accounts and scientific monitoring of similar events confirm that the color change at the surface of a submarine eruption can appear within minutes of the vent opening. The temperature of the water in the immediate area rises rapidly. Fish and marine life in the zone experience sudden, extreme changes to their environment. Acidity spikes, oxygen levels drop. The chemical balance the ocean maintains for life collapses locally in a short period. There is also a pressure wave component. Each underground explosion sends a pulse of pressure upward through the water column. When that pulse reaches the surface, it causes the water to heave upward and then fall back. The repeated heaving is what produces the churning, boiling appearance Kennedy observed. The surface is responding to pressure pulses arriving from below, not from any surface weather or current. The color of the water above the vent also tells scientists something specific. Dark brown-gray discoloration usually means high ash and rock fragment content in the rising column. Blue-green discoloration sometimes indicates dissolved volcanic sulfur compounds mixing with the water. White or milky discoloration can indicate high levels of dissolved minerals. Scientists monitoring the Bismarck Sea eruption from satellite reported discolored water spreading outward from the eruption site in the days following May 8th. That spreading discoloration was visible from orbit, even when the ash plume itself was hidden by cloud cover. The The zone of changed water around a submarine eruption is also biologically devastating in the short term. The fish that floated dead to the surface the morning after the main eruption were killed by this transformation. Temperature shock, chemical shock, pressure shock from the explosions directly below them. The ocean in that zone went from a functioning marine habitat to an uninhabitable zone in a matter of hours. Kennedy saw the surface of that transformation from above. The fish saw it from inside. What came up from below the next morning was a visible record of what the eruption had done underwater. Think about what ash has to defeat to reach the surface. Volcanic ash is not the same as the ash from a fire. Fire ash is light, dry, and barely weighs anything. Volcanic ash is pulverized rock. When an eruption happens, the enormous heat and pressure involved shatters solid rock into tiny fragments. Those fragments range from fine particles, smaller than a grain of sand, to larger chunks the size of gravel. The finest particles are called volcanic ash. They are dense enough to sink in water, not float. So how does ash from a vent 1,600 to 4,000 feet below the ocean surface make it up to open air? The answer is force. The gas content of rising magma is the engine. When magma rises from deep underground toward the surface, the pressure on it decreases. As pressure drops, the dissolved gases inside the magma expand rapidly, violently. This is the same principle as opening a shaken soda bottle. The moment the seal breaks and pressure drops, the gas forces its way out, and it takes the liquid with it. At a submarine volcanic vent, the gas expansion happens inside a column of rising magma. The expansion is explosive. The force generated is enormous, enough to accelerate the surrounding material upward at high speed. That upward velocity is what drives the ash through the water column. The gas is essentially acting as a propellant, launching the fragmented rock particles upward against gravity and against the resistance of dense ocean water. Dense ocean water resists this movement. Water is heavy, and pushing solid rock particles through it requires sustained force. The ascending column of material loses velocity as it rises, shedding ash particles into the surrounding water at various heights. The finest particles, the ones light enough to stay suspended even after losing most of their upward momentum, continue rising on the thermal current produced by the heat of the column. The heaviest fragments fall back toward the seafloor. The ash that actually breaks the surface is the material that managed to maintain enough upward momentum for the entire journey. At a vent depth of 1,600 feet, at a depth of 4,000 feet, the confirmed upper estimate for this eruption, it is remarkable. The pressure at 4,000 feet of ocean depth is roughly 100 times the atmospheric pressure at sea level. The eruption at the central Bismarck Sea forced material through that pressure column and broke the surface with enough energy to produce a visible column rising 9,000 feet above sea level, according to theory from scientists monitoring the event. 9,000 feet above the ocean. That is higher than most of the mountains in the eastern United States. The ash column was visible to passing aircraft and to local fishermen across a wide area. It was also the first surface feature that satellites were attempting to track, though cloud cover would soon interfere with that effort in a way nobody anticipated. The ash was the most visible sign of the eruption, but the thing floating on the surface around it told a different story about what was happening below. Satellites see almost everything. That is the assumption. Sensors orbiting Earth can detect a wildfire burning in a forest the size of a football field. They can measure ocean temperature to a fraction of a degree. They can track a ship crossing an empty ocean by its heat signature alone. Modern Earth observation satellites are extraordinary instruments, and the global monitoring network built on top of them gives scientists a near real-time picture of the planet's surface, except when there are clouds. The Bismarck Sea sits in one of the cloudiest regions on Earth. The western tropical Pacific generates enormous persistent cloud systems driven by warm ocean temperatures and rising humid air. Satellite observation of this region is routinely blocked for days at a time by cloud cover that extends from near the ocean surface to high in the atmosphere. The clouds are thick enough to block visible light imaging and in some cases thermal infrared imaging as well. When the central Bismarck Sea volcano erupted on May 8, 2026, orbiting satellites picked up the initial thermal signature and the first hours of the ash plume. Confirmed. The Mineral Resources Authority in Papua New Guinea confirmed this. Then the cloud cover closed in. For several days following the initial detection, continuous satellite tracking of the eruption was blocked. The ash plume, the discolored water, the thermal anomaly above the vent, all of it was hidden beneath a thick layer of tropical cloud. Scientists watching from orbit could not confirm whether the eruption was accelerating, maintaining, or slowing down. They could not measure the spread of the ash column. They could not monitor the extent of the discolored water zone. This forced a shift in how the event was being tracked. Instead of satellite imagery, authorities relied primarily on seismic data coming in from ground sensors across Papua New Guinea and the broader Pacific network, and they relied on reports from ships and fishermen who were close enough to observe directly. Eyewitness accounts became scientific data. Kennedy Massis and other mariners in the area were, for several days, the most reliable source of ground truth information available to the agencies trying to understand what the volcano was doing. This situation exposed something uncomfortable. A major geological event was happening in an ocean region used by fishing communities and commercial shipping routes, and the world's most advanced monitoring systems were blinded by weather for days. The gap between what we assume our technology can see and what it actually sees in real-world conditions is significant. This is not an isolated failure, it is a structural limitation. Tropical oceans, the regions most likely to host active submarine volcanoes due to their tectonic settings, are also the regions where cloud cover most reliably blocks satellite observation. The places we most need to monitor are the places our orbital systems struggle most to see. Authorities managing the event acknowledged this directly. The Mineral Resources Authority stated that cloud cover forced them to depend more heavily on seismic and maritime data to track the ash column spread. That combination of data sources is slower, less precise, and dependent on human observers being close to a potentially dangerous zone. The satellites were up there, orbiting, watching, collecting data. The clouds were in the way, and below the clouds, the ocean kept doing what it was doing. Two sets of experts looked at the same eruption. They did not agree on something fundamental: the depth of the vent. Steve Saunders, the chief geodetic surveyor at the Rabaul Volcano Observatory, placed the ocean depth in the eruption area between 1,600 and 2,600 feet. The Rabaul Volcano Observatory is the official monitoring authority for volcanic activity in Papua New Guinea. Confirmed, their measurements come from existing seafloor surveys of the region, the most current official data available for the central Bismarck Sea. Independent analysts tracking the eruption through separate data streams reported a different figure. Their estimates placed the vent as deep as 4,200 feet below the ocean surface. That is theory, drawn from independent tracking data and alternative seismic analysis, and it has not been confirmed by the official monitoring body. The difference between 1,600 feet and 4,200 feet seems like a detail. It is more than that. Depth determines pressure. At 1,600 feet, the water pressure above the vent is roughly 50 times the pressure you feel standing at sea level. At 4,200 feet, that pressure is closer to 130 times sea level pressure. The force required to push volcanic material upward through those two environments is dramatically different. A vent at 4,200 feet has to generate far more explosive energy to break the surface at all. Depth also affects the chemistry of what reaches the surface. At greater depths, gases that would normally expand and drive the eruption stay dissolved in the magma longer because the pressure keeps them compressed. When the magma finally rises high enough for the pressure to drop, the gas release is more sudden and more violent. Deeper vents tend to produce more explosive eruptions when they do break the surface, because the gas has been compressed for longer during the ascent. Depth affects the early warning timeline. A vent at 1,600 feet starts producing surface signals faster than a vent at 4,200 feet, because the material has less distance to travel. If the vent is deeper than official estimates suggest, the time between a seismic trigger event and visible surface eruption is longer. That extra time could be critical for a warning system trying to alert maritime traffic. The reason for the discrepancy between the official and independent measurements comes down to data sources. The Rabaul Volcano Observatory's depth figures come from existing seafloor surveys, charts that may predate detailed modern sonar mapping of this specific area. The central Bismarck Sea seafloor is poorly mapped overall. Independent analysts using seismic wave travel times and acoustic data to calculate depth may be working with more specific information from the eruption itself. Neither number is definitively wrong. The true depth may fall somewhere between the two estimates. A marine survey of the site, using sonar mapping from a research vessel, could resolve the question. That survey has not yet been possible because the eruption is ongoing and the exclusion zone around the site remains active. A measurement disagreement between official and independent scientists might seem like an academic argument. Over a live eruption that could affect maritime traffic and coastal communities, knowing the exact depth of the vent is a real operational question with real consequences. The answer is still unknown. Something unusual appeared on the ocean surface around the eruption site. Rocks that float. Pumice looks like ordinary grey stone. Pick it up, and it feels lighter than it should. Drop it in water, and it stays on top. Pumice is volcanic rock that formed when magma loaded with trapped gas cooled so fast that the gas could not escape. Instead of forming bubbles that popped and released, the gas froze in place inside the solidifying rock, creating millions of tiny air pockets throughout the material. The result is a rock that is more air than solid, a stone with the density of something that should sink, but the structure of something that floats. Finding pumice on the ocean surface above a submarine eruption carries a specific meaning that scientists pay close attention to. For pumice to appear floating on the surface, it had to form somewhere below, be ejected from the vent, and travel upward through the water column. Pumice forms when magma cools rapidly in contact with cold water. At a deep vent, the intense pressure and cold ocean water surrounding the rising magma create exactly those conditions. The magma erupts, meets cold water, cools rapidly, and the gas-rich outer layers freeze into pumice, while the core is still hot. The presence of floating pumice tells scientists several things. First, the magma reaching the surface has high gas content. Gas-rich magma forms pumice. Gas-rich magma also tends to produce more explosive eruptions because the gas expansion on ascent is more violent. Second, the amount of pumice provides a rough sense of the eruption volume. More pumice means more material is being ejected. Third, and most significant for what comes next, the pumice distribution pattern tells scientists something about the shape of what is forming below. Steve Saunders, the chief surveyor at the Rabaul Volcano Observatory, confirmed that the presence of floating pumice at this site indicates a cone is probably forming close to the surface. That is a theory, not a confirmed measurement, because nobody has yet seen the seafloor directly. But the reasoning is sound. When a submarine eruption continues over days and weeks, the ejected material does not all float away. A large portion falls back toward the vent and piles up. Each eruption adds another layer. The structure grows upward from the seafloor. This is how an underwater mountain builds itself. The pumice rafts drifting on the surface around the eruption site are the lightweight debris of that construction project. The heavier material fell back and stayed. Somewhere below the surface, the seafloor in the central Bismarck Sea now looks different than it did before May the 8th. A mound of newly deposited volcanic material has been accumulating around the vent. With enough time and sustained eruption, that mound grows into a cone. The cone grows into a seamount. The seamount, if the eruption continues long enough and with enough force, eventually breaks the ocean surface. The pumice floating outward from the site on ocean currents is the visible sign of a hidden construction happening below. What is being built down there, and how fast it is growing, remains completely unknown. Right now, the ocean floor in the central Bismarck Sea is changing shape. Nobody can see it. The water above the site is too deep, too turbulent, and too dangerous for divers or remotely operated vehicles to approach during an active eruption. Satellites cannot see through the ocean. Sonar mapping requires a ship positioned directly above the site, which the Maritime Exclusion Zone currently prevents. The construction happening below the surface is real and ongoing, and it is happening in complete darkness with no human observer. Here is what science tells us is occurring based on confirmed observations from comparable events. Each explosion from the vent launches material in all directions. The gas-driven blasts carry volcanic material upward, but much of what goes up comes back down. The heaviest rock fragments follow ballistic paths and land close to the vent. The medium-sized material settles slightly farther out. The finest ash travels farthest before settling. Over days and weeks of sustained eruption, the material landing closest to the vent accumulates. Layer by layer, the pile grows. This process is slow by human standards and rapid by geological ones. A submarine volcano sustaining the level of activity described at the Bismarck Sea site can add dozens of feet of height to a growing cone over the course of weeks. Scientists have confirmed this rate in events like the Havre Seamount eruption near New Zealand, where a single eruptive phase deposited an enormous volume of material on the seafloor in a short period. The geometry of the growth matters. Volcanic material piling around a central vent naturally forms a cone shape because it lands closest to the vent at the bottom and spreads outward as the pile grows. The cone builds upward toward the ocean surface, narrowing as it rises. If the eruption maintains consistent output, the cone continues gaining height. Pumice confirms this process is underway at the Bismarck Sea site. Steve Saunders' assessment that a cone is probably forming close to the surface is a reasonable inference from the volume and character of the floating pumice observed. Theory, but grounded in direct comparable evidence from other submarine eruptions. The cone growing below is also reshaping the currents around it. A large structure rising from the seafloor alters how water flows through the area. It creates turbulence, changes the local thermal profile of the water, and disrupts the habitat of anything living on or near the seafloor around it. For a geological event, this is moving fast. For a human watching from a ship, it would be invisible because the change is happening below hundreds of feet of disturbed, discolored water. The closest humans have gotten to watching a moment like this unfold in real time was during the formation of the volcanic island of Surtsey off the coast of Iceland in 1963. That event began exactly the same way. A submarine eruption, ash columns breaking the surface, pumice rafts drifting outward. Within 4 days, the material had piled high enough to emerge from the ocean. Whether the central Bismarck Sea site will reach that threshold depends entirely on how much material remains in the chamber below, and nobody knows that number yet. The morning after the main eruption, the fishermen who approached the site found something that made the scale of the event clear in a way that numbers cannot. Dead fish. Thousands of them, floating across the surface in every direction from the eruption point. This is confirmed. Eyewitnesses reported massive quantities of dead fish covering the water near the active site on the day following the initial explosion. The image is striking, and it tells a precise story about what the water column experienced during the eruption. Fish in the open ocean are built for their specific depth. Their bodies are calibrated to the pressure, temperature, and chemical composition of the water they inhabit. When all three of those factors change simultaneously, rapidly, and to extremes, the result is death. That is what the eruption produced in the water column above the vent. The pressure waves alone were enough to kill. Each explosion from the vent sent a pulse of pressure radiating outward through the water in all directions. A pressure wave that strong, passing through a fish's body, ruptures internal organs. The swim bladder, a gas-filled sackfish used to control their buoyancy, is especially vulnerable. A rapid pressure spike causes it to expand or rupture explosively. Fish with ruptured swim bladders cannot control their position in the water and float to the surface. The temperature shock added another mechanism. The superheated water rising from the vent dramatically elevated local water temperatures in a short period. Fish caught in the rapidly warming zone died from thermal shock before they could swim out of range. Cold water fish and deep water species that had never experienced temperatures anywhere near those produced by volcanic activity had no physiological tolerance for the change. The chemical shift was the third mechanism. Volcanic gases dissolving into the ocean water around the vent dropped oxygen levels rapidly in that zone. Carbon dioxide, sulfur dioxide, and hydrogen sulfide pouring from the eruption chemically altered the water composition. Fish require dissolved oxygen to breathe through their gills. Strip that oxygen out of the water and replace it with volcanic gases, and suffocation follows quickly. The combined effect of pressure, heat, and chemical change killed marine life across a wide area around the vent in a short window of time. The bodies floated to the surface because the same buoyancy physics that keep fish at their operating depth, once disrupted, sends them upward. Scientists treat mass fish kill events near submarine eruptions as diagnostic data. The distribution of dead fish across the surface gives an approximate map of how far the lethal zone extended from the vent. The species composition of the dead fish tells scientists roughly what depth range the eruption impacted most severely. The Bismarck sea fish kill has not been formally studied yet. The eruption is ongoing. The exclusion zone prevents close approach. The ecological documentation will come later, when conditions allow. For the communities of fishermen who work these waters, the fish kill carries a different kind of weight. The tuna population in this region provides income and food for coastal towns across Papua New Guinea. The long-term effect of this eruption on that population remains completely unknown. What happened to the ocean above the vent is visible and immediate. What is happening to the geology below is something much harder to measure. And the next comparison that scientists reached for when assessing the risk of this eruption involves an event from more than a century ago that ended with entire villages swept into the sea. 124 miles south of where Kennedy Massis saw the ocean boil, there is a remnant of something that used to be much bigger: Ritter Island. In 1888, Ritter Island was a volcanic peak rising above the ocean surface, a proper island, with a mountain above the waterline and a massive structure extending down through the ocean floor below. It sat in the Bismarck Sea region, part of the same tectonic zone, shaped by the same underlying geological forces that created the submarine ridge now erupting to the north. On March 13, 1888, the flank of Ritter Island collapsed. A flank collapse is when the side of a volcanic structure gives way. The material does not just slide down gradually, it falls. A massive section of the island, estimated at roughly 1 cubic mile of rock, dropped into the ocean in a very short period. When that volume of rock displaces ocean water at that speed, the water has to go somewhere. It moves outward in all directions at enormous speed. The wave generated by the Ritter Island collapse reached the coastlines of nearby islands within minutes. The confirmed historical record shows that tsunami devastated coastal communities across the region. Villages were swept away. Hundreds of people died. The wave reached Papua New Guinea and surrounding islands with force that destroyed everything near the waterline. What remains of Ritter Island today is a much smaller remnant. The collapsed section is gone. The island lost a substantial portion of its mass in 1888 and has never recovered it. The scar on the seafloor from the collapse is still visible in sonar surveys of the area. Scientists confirmed the Ritter Island collapse as one of the largest volcanic flank collapses recorded in the Pacific in the last few centuries. The reason this matters to the current eruption is geological proximity and structural similarity. Independent analysts have pointed to the Ritter Island event when discussing the worst-case scenarios for the newly active Bismarck Sea vent. The two structures sit in the same tectonic zone, share similar seafloor geology, and both involve volcanic edifices built from accumulated erupted material. A submarine cone growing from sustained eruption, as appears to be happening at the current site, accumulates mass over time. The structural integrity of a rapidly growing cone has not been tested by the same geological timescale that stabilizes older volcanic structures. The official position from the Rabaul Volcano Observatory is that a flank collapse at the current site is a worst-case scenario, with a low probability. That is the confirmed assessment from the primary authority monitoring this event. Independent researchers consider it a genuine possibility worth serious attention, given the proximity of the Ritter Island precedent. Both views are on record. The official assessment carries more institutional weight. The independent concern carries historical gravity. What happened at Ritter Island in 1888 was real. The wave was real, the deaths were real, and the seafloor south of the current eruption site still carries the shape of that collapse. The question scientists are now debating is whether the structure forming below the central Bismarck Sea carries any of the same risks. And that question is harder to answer than it sounds. The debate has two sides. Both sides have legitimate reasons for their position. Start with the official view. The Rabaul Volcano Observatory, the confirmed primary authority for monitoring volcanic activity in Papua New Guinea, assessed the risk of a major coastal tsunami from the current eruption as minimal. Steve Saunders stated directly that the distance of the eruption site from the nearest coastline, 62 miles, provides a significant buffer. A moderate underwater collapse or explosive event at that distance would generate wave energy, but the energy would dissipate considerably before reaching populated coastal areas. The observatory acknowledged that more vigorous explosive activity could produce minor, localized wave action in the immediate area around the vent. But a Ritter Island-scale event threatening distant coastlines, in their assessment, carries a low probability. That is the official position. The Pacific Tsunami Warning Center confirmed it did not issue a basin-wide alert at any point during the eruption. Confirmed. That system exists to trigger warnings when the data supports a genuine regional threat. The data from this event did not meet that threshold. Now the independent view. Several researchers outside the official monitoring structure have pointed to specific factors that in their analysis make a flank collapse at the current site worth taking seriously. The first factor is the seafloor geology. The central Bismarck Sea sits on microplate boundaries that are moving rapidly by geological standards. The fault systems in this area generate frequent significant earthquakes. A structure growing on top of an active fault system is building on unstable ground. Confirmed, the tectonic setting here is one of the most complex in the Pacific. The second factor is the growth rate. A cone that has been growing rapidly from a sustained eruption has not had time to consolidate. Older volcanic edifices are denser, more compacted, and more internally stable, because millennia of geological pressure have welded their component layers together. A newly formed cone is looser. The material is freshly deposited, not yet cemented by pressure and time. Independent analysts argue this makes the current structure more vulnerable to collapse than a mature volcanic edifice would be. The third factor is the Ritter Island geometry. When analysts look at the seafloor maps of the region, they see that the Ritter Island collapse happened along a specific slope angle and fault orientation. The current eruption site sits along fault lines with comparable orientations, Whether this geometrical similarity translates to comparable collapse risk is disputed, but the parallel is what drives the concern. The official and independent positions are both scientifically defensible. The official assessment is grounded in current data and the absence of imminent threat signals. The independent concern is grounded in historical precedent and structural vulnerability arguments. The honest answer is that the newly forming structure below the central Bismarck Sea has never been mapped. Nobody has seen its shape, measured its slope, or assessed its internal structure. The seafloor there looks different today than it did before May 8th. How different, and what that difference means for stability, remains completely unknown. A marine survey would resolve many of these questions. That survey is not currently possible. The Pacific Tsunami Warning Center is watching the seismic data. The Rabaul Volcano Observatory is tracking the acoustic and surface signals. Independent researchers are running their models. And below 62 miles of open ocean, the volcano keeps building upward. What the broader tectonic picture looks like and whether this eruption is connected to a larger pattern of Pacific instability is a question that pushes the stakes even higher. The Pacific Tsunami Warning Center has one job: watch the ocean, detect the signals, warn the people in time. It does that job through a network of seismic stations, seafloor pressure sensors, called tsunami buoys, and tide gauges positioned across the Pacific Basin. When an underwater event generates a wave large enough to threaten distant coastlines, that network picks up the signal. The center analyzes it in minutes and issues alerts to governments across the Pacific within a window designed to give coastal populations time to evacuate. When the central Bismarck Sea erupted on May 8th, the center was watching. The seismic event registered across their network. The eruption activity was noted. No basin-wide alert was issued. Confirmed. Here is why, and what the threshold actually looks like. The center evaluates several factors simultaneously when deciding whether to issue a warning: the magnitude and type of the seismic event, the depth and character of any seafloor displacement, the presence or absence of wave signals on nearby buoys, the location of the event relative to population centers. A magnitude 5.4 earthquake, even one triggering a volcanic eruption, falls below the seismic threshold that automatically triggers a tsunami alert. Earthquakes in the magnitude 7 and above range, particularly those involving vertical seafloor displacement across large fault areas, generate the most dangerous tsunamis. The May 8th event did not reach that magnitude. The volcanic eruption itself added complexity. Eruptions can generate local wave action, as Saunders confirmed, but the mechanisms are different from a major fault rupture. A volcanic eruption pushes material upward through a relatively small vent area. The seafloor displacement is localized. The water disturbance it creates is intense near the source but loses energy quickly with distance. Compare that to a major fault rupture, where a section of seafloor hundreds of miles long shifts by several feet in seconds, displacing an enormous volume of water simultaneously across that entire length. The threshold for a basin-wide alert requires a confirmed large-scale seafloor displacement event. The Bismarck Sea eruption did not produce that signature on the buoy network. The nearby tide gauges did not register anomalous wave behavior beyond what local disturbance would produce. The scenario that would change that calculation involves a flank collapse. If a significant section of the forming submarine cone collapsed rapidly and displaced a large volume of water, in a short time, the buoy network would pick up the resulting wave signal. That signal would trigger the center's analysis protocol. If the wave amplitude and travel speed matched a genuine tsunami threat, an alert would follow. That has not happened. The buoys around the Bismarck Sea have not registered that kind of signal, but the center is watching in real time, and the seismic monitoring of the site remains active. A sudden escalation in earthquake activity around the vent, particularly the kind of swarm that precedes a structural failure, would immediately elevate the alert status. The system is designed for exactly this kind of prolonged monitoring. It waits for the threshold until the data crosses it The default position is observation. 62 miles of open ocean between the vent and the coast provides time. That time is the buffer the center is relying on. Whether that buffer is enough depends on what happens next underground. Monitoring this eruption is one of the stranger problems in modern emergency management. The Rabaul Volcano Observatory is the official body responsible for tracking this event. They are experienced. Papua New Guinea sits on one of the most volcanically active arcs on Earth, and the observatory maintains a professional operation capable of responding to complex geological crises. But this specific eruption presents a combination of challenges that tests every monitoring system available. The vent is underwater, deep underwater. No ground sensors can be placed directly on it. The closest seismometer installations are on land, on islands dozens of miles from the eruption site. They pick up the seismic signals from the event, but the data they receive has traveled through miles of ocean crust and water before arriving. That travel path introduces noise and reduces precision. The satellite coverage is intermittent due to cloud cover, as confirmed by the Mineral Resources Authority. When clouds clear, satellites provide thermal imaging of the surface above the vent and visual confirmation of the ash plume. When clouds return, that data disappears. The acoustic monitoring network picks up the underground explosion signals. Scientists can track the rhythm and intensity of the explosions through acoustic data and infer whether the eruption is intensifying or weakening. But acoustic data alone does not reveal the shape, size, or growth rate of what is forming on the seafloor. Maritime reports fill the remaining gaps. Fishermen, Coast Guard vessels, and any other ships transiting the area provide human observation of the surface conditions. Kennedy Massis was the first of these. In the days following the eruption, other mariners contributed reports on the ash plume height, the extent of discolored water, and the presence of pumice on the surface. These observations are imprecise and inconsistent, but they are real-time and ground-truthed in a way satellite data cannot be. The Mineral Resources Authority has been issuing regular updates based on this patchwork of information sources. Each update combines seismic data, available satellite imagery, acoustic monitoring, and maritime observations into a picture that is genuinely incomplete but represents the best available information. There is no single instrument providing a continuous, clear feed of what the volcano is doing. This situation is not unique to Papua New Guinea. Monitoring an active submarine volcano in a remote, cloud-prone ocean region pushes the limits of what current technology can do from a distance. A research vessel equipped with sonar, underwater vehicles, and direct scientific instruments would provide vastly more detailed information. That kind of deployment takes time to organize, requires a gap in active dangerous eruption activity, and depends on the exclusion zone being lifted. The observatory is managing the event with what they have: seismic networks, intermittent satellite data, ship reports, models, experience from monitoring other volcanic systems in the region. It is remarkably thin coverage for an event this significant, and beyond the monitoring gap, there is a human consequence that the data systems cannot capture at all. A maritime exclusion zone sounds like a bureaucratic term. For Kennedy Massis, it means he cannot go back to where he fishes. An exclusion zone around an active submarine eruption is a defined area of ocean that authorities have declared off-limits to navigation. The reasons are practical and serious. The eruption produces unpredictable currents from the upwelling heat and material. It generates chaotic wave action as underwater explosions push water upward in irregular bursts. Ash and volcanic debris in the water can damage boat engines and propulsion systems. Sulfuric gases breaking the surface create zones of air that are chemically hazardous to breathe. A sudden escalation in explosive activity could produce a localized wave capable of overturning a small vessel without warning. Papua New Guinea authorities issued direct warnings for unpredictable waves and chaotic currents. Confirmed. The area around the eruption site, became a zone that fishing vessels were strongly advised to avoid. The central Bismarck Sea is a commercially critical fishing ground. The tuna populations in this region support a substantial portion of the fishing economy for Papua New Guinea and surrounding island communities. Industrial fishing fleets operate here. Small-scale commercial fishermen like Kennedy Massis work these waters as their primary source of income. Subsistence fishing communities along the coast depend on the catches that come from this part of the ocean. An exclusion zone does not compensate anyone for lost income. It is a safety measure, and the authorities issuing it are making the correct call given the genuine hazards present. But for a fisherman whose boat, fuel costs, and daily income all revolve around access to a specific stretch of ocean, the zone is economically devastating in the immediate term. The fish kill that followed the eruption adds another layer. The marine habitat directly around the vent was disrupted severely in the first days. Dead fish floating on the surface represent lost catch, but they also represent a disruption to the local marine ecosystem that extends beyond the immediate aftermath. Tuna do not stay in waters where the chemical and thermal conditions have been altered. They move. Where they go, and when or whether they return to the areas around the eruption site, is completely unknown. The long-term effect on the regional tuna population remains undocumented. Confirmed, scientists have not been able to assess it because the eruption is ongoing and the area is restricted. For fishing communities that run on tight margins, uncertainty of this duration is its own kind of crisis. The exclusion zone will remain in place until the seismic swarm associated with the eruption subsides to a level that authorities consider safe for maritime traffic. There is no fixed timeline for that. Eruptions like this one can sustain active phases for weeks or extend over months. The volcanic system controls the schedule. The fishermen wait. Meanwhile, the scientific debate about what is happening in the broader Pacific tectonic picture around this eruption has been building its own kind of intensity. Some independent researchers have been watching the Western Pacific with growing unease. Their argument goes like this: the Bismarck Sea eruption did not happen in isolation. In the weeks surrounding the May 8th event, other volcanic and seismic activity across the Western Pacific was running above baseline. Multiple volcanoes in the region showed elevated activity simultaneously. Earthquake swarms occurred in separate zones across the Pacific Arc. To some researchers, the pattern looked like a system under elevated stress, responding across multiple points at once. Their conclusion, presented as theory and not confirmed by any major geological institution, is that the Pacific Plate is entering a period of heightened activity, a phase where the slow grinding mechanics of plate movement are expressing themselves through more frequent and more intense surface events. Official geological surveys reject this framing. The position of major geological institutions is that the regional eruptions and earthquakes occurring around the same time as the Bismarck Sea event are independent events. They share a tectonic setting, the Pacific Ring of Fire, which is always active. Elevated activity at multiple sites simultaneously does not, in the official scientific view, constitute evidence of a coordinated plate-wide stress response. The geology does not work that way at the scale of a single month or even a single year. Plate dynamics operate across millennia. The disagreement is about scale and interpretation. Independent researchers are looking at a window of weeks and seeing a pattern. Official geologists are looking at a window of millions of years and seeing noise. Both groups are using real data. They are reaching different conclusions because they are asking different questions. The independent researchers are asking, does this cluster of events indicate something unusual is happening right now? The official position answers, clusters of events are normal within highly active tectonic zones and do not require a unified explanation. Who is right depends on what the next months show. If the elevated activity across the Western Pacific continues and intensifies, the independent researchers will have grounds for a stronger argument. If the activity normalizes back to baseline after these events resolve, the official position will be confirmed. There is a reason the independent view gets attention even without official endorsement. The Ring of Fire is not a static system. It has produced periods of heightened global volcanic and seismic activity in the past. Scientists have documented historical clusters where multiple major events occurred in close temporal proximity. Whether those clusters reflect a connected system response or random coincidence within a perpetually active zone is a genuine scientific debate with a long history. For the communities living along the Pacific Arc, the distinction between connected system and random coincidence carries real stakes. A random event is survivable. A connected sequence, where one rupture increases stress on adjacent fault systems, potentially producing cascading events, is a different kind of problem. The Bismarck Sea eruption sits inside this larger argument, an active data point in a debate about how the Pacific system behaves. The geology beneath the Bismarck Sea that makes this argument relevant goes deeper than just the surface eruption, and understanding it reveals why this region keeps producing events that force scientists to revise their assumptions. The Pacific Ring of Fire runs roughly 35,000 miles around the Pacific Ocean basin. Along that arc, approximately 90% of the world's earthquakes occur. 3/4 of all active volcanoes on Earth sit inside it or immediately adjacent to it. The ring exists because the Pacific Ocean is ringed by subduction zones, places where oceanic plates are being pulled beneath continental plates or other oceanic plates, releasing enormous energy as they go. In the weeks surrounding the central Bismarck Sea eruption of May 8, 2026, monitoring networks across the Western Pacific logged elevated activity. Multiple volcanic systems in the Western Pacific Island arc showed increased output. Seismic swarms appeared in separate locations. The Bismarck Sea event was the most dramatic surface expression, but it was not a completely isolated spike in an otherwise quiet region. Scientists track what is called background activity for every monitored zone. Background is the normal range of earthquake frequency, magnitude, and volcanic output for a region given its tectonic setting. Deviations above background in a region like the Western Pacific are not automatically alarming because the Ring of Fire produces significant events regularly, but deviations at multiple locations within a compressed time window are noted and analyzed. The cluster of events in recent weeks registers as above background for the Western Pacific Island arc zone, confirmed in the sense that monitoring data shows elevated numbers. The interpretation of that elevation is where scientific opinion splits. The mechanism that could theoretically link separate events along a tectonic arc is called stress transfer. When a fault ruptures, it does not simply release its own stored energy. It changes the stress distribution on adjacent fault segments. A rupture on one section of a fault system can increase the load on a neighboring locked section, moving it closer to its own failure threshold. This is a confirmed geological process. Scientists have documented it in major earthquake sequences globally, including aftershock patterns and triggered events on separate fault systems. The question applied to the Western Pacific cluster is whether the events in the weeks around the Bismarck Sea eruption represent stress transfer moving along the arc, or whether they represent coincidental independent releases from a perpetually stressed system. Official geological bodies consider the independent release explanation more consistent with the data. The events are separated by enough distance, and the fault systems involved are different enough in character that a direct stress transfer chain is not the most supported explanation. Independent researchers argue that the arc is more mechanically connected than official models suggest, and that the surface events we see are expressions of a deeper pressure redistribution happening in the mantle beneath the plate. Neither position can be immediately confirmed or refuted with the data currently available. The instruments exist to gather relevant data. The analysis takes time. What is confirmed is that the Bismarck Sea does not sit in a quiet corner of the planet. It sits at the intersection of some of the most mechanically complex geology on Earth, in a region that has been producing extreme events for millions of years. Understanding the specific structure of that geology reveals why this particular region keeps surprising scientists. Smaller is more dangerous. The major tectonic plates that most people learn about: the Pacific Plate, the North American Plate, the Eurasian Plate, are enormous. The Pacific Plate covers an area larger than all of Earth's continents combined. Plates that size move slowly. Their mass creates inertia. They grind against each other with enormous force, but at a pace measured in inches per year. The Bismarck Sea sits on a fundamentally different scale. The region directly beneath the Bismarck Sea is occupied by two primary microplates: the South Bismarck Plate. These are small fragments of crust, geologically young and mechanically unstable. Scientists have confirmed that microplates in this zone move faster than the surrounding major plates. The velocity difference is significant. While the Pacific Plate moves a few inches per year, microplates in complex boundary zones like the Bismarck Sea can move at rates several times faster. Faster movement means more frequent ruptures. A plate moving quickly along a boundary with another plate accumulates and releases stress more often. The interval between major earthquakes on a fast-moving microplate boundary is shorter than on a slow-moving major plate boundary. The Bismarck Sea region produces significant earthquakes with a frequency that reflects this accelerated cycle. But the connection to volcanic violence runs deeper than just earthquake frequency. Faster plate movement at a subduction zone means faster delivery of crustal material into the mantle below. As oceanic crust subducts and sinks, it releases water trapped in its minerals at depth. That water lowers the melting point of the surrounding mantle rock, producing magma. More crust subducting faster produces more magma more quickly. The magma rises and collects in chambers beneath the volcanic arc above. The Bismarck Sea region's fast-moving microplate system effectively runs a more intense version of the subduction factory compared to slower plate boundaries. More magma production, more pressure in the chambers, more frequent volcanic events, more explosive eruptions when they occur. The central Bismarck Sea fissure ridge, the one that erupted in May 2026, sits directly above this system. The magma that forced its way through the seafloor on May 8th came from a source that has been continuously replenished by the fast subduction below. The 54 years of dormancy between the 1972 detection and the current eruption did not mean the magma system was inactive. It means the chamber was refilling. A 54-year reload cycle on a fast-moving microplate system is, geologically, relatively short. The chamber fills, seals, pressurizes, waits for a structural trigger, and releases. The trigger arrived on May 8th in the form of a magnitude 5.4 rupture. The speed of the microplate system beneath the Bismarck Sea is also why the seafloor here is so poorly understood. Rapid plate movement reshapes the seafloor faster than survey expeditions can keep up with. Maps made a decade ago may not accurately reflect the current topography of the basin. The structures formed by fast microplate tectonics are younger, less studied, and less predictable than the geology of slower-moving regions. That poor understanding has direct consequences for what scientists know and do not know about the current eruption's source. Scientists have mapped the surface of Mars in more detail than the floor of the Bismarck Sea. That comparison is not rhetorical. It is a confirmed fact about the state of ocean floor mapping. Mars has been surveyed by orbiting spacecraft using radar altimetry that can resolve surface features a few hundred feet across the entire planet. The ocean floor, covered by miles of water that blocked radar and visible light, requires ships to map it directly using sonar. Ships are slow, expensive, and limited in number. The ocean is vast. Approximately 20% of the global ocean floor has been mapped at high resolution. The remaining 80% is known only at scales too coarse to reveal the specific fault structures, vent locations, and geological details that matter for understanding events like the Bismarck Sea eruption. The central Bismarck Sea falls into the poorly mapped category. The general shape of the seafloor basin is known from older surveys. The existence of a fissure ridge in the eruption area was confirmed by the acoustic detection in 1972, but the detailed topography of that ridge, the precise orientation of the fault lines feeding it, the depth profile of the vent itself, and the geometry of the magma chamber below are all unknown. Scientists working this eruption are making decisions with a geological map that has enormous blank spaces in exactly the area that matters most. This matters operationally. Knowing the fault orientation tells scientists which direction any flank collapse would travel and where the resulting wave energy would be directed. Knowing the precise depth of the vent changes the models for eruption intensity and gas behavior. Knowing the topography of the seafloor around the vent affects predictions about how the growing cone will shape itself and what its stability margins are. None of that information exists for this site in the detail the current situation demands. The tools to fill these gaps exist. Multi-beam sonar mapping from a surface ship can resolve seafloor features down to a few feet over wide areas. Autonomous underwater vehicles can map at even higher resolution, at close range. A well-equipped research vessel deployed to the Bismarck Sea after the current active phase subsides could produce a detailed map of the new seafloor topography in a matter of weeks. That survey would answer questions that are currently unknown. How large is the cone that formed during this eruption? What is its slope geometry? What do the fault lines around it look like? And how stable is the structure? The fundamental reason this survey has not happened yet is simple. The eruption is ongoing. Sending research equipment into an active exclusion zone is not feasible during the dangerous phase. The science waits until the geology cooperates. The broader lesson extends beyond this specific event. The ocean floor holds thousands of volcanic structures in various states of dormancy, with unknown histories, unknown chamber sizes, and unknown stability. The number of structures comparable to the central Bismarck Sea fissure ridge that have never been detected, never recorded a single eruption, and are building pressure in unmapped chambers is genuinely unknown. What woke up on May 8th was the one humans knew about, even if barely. What else is down there, building quietly in the dark, is a question the ocean has not answered. History has given us a few glimpses of what birth looks like at geological scale. A cook on a fishing trawler off the southern coast of Iceland looked over the side and saw the ocean smoking. He assumed it was a ship on fire below the horizon. Then the smoke thickened, then ash started rising. Then a column broke the surface with enough force to be heard. Within 4 days, solid ground appeared above the ocean. Within 3 weeks, it was a recognizable island. By the time the eruption finished, 3.5 years later, the island of Surtsey stood 1,000 square feet above the ocean's surface and covered more than a square mile of ocean that had previously been open water. Scientists watched the entire process. They documented the formation of black lava beaches, the first bacterial mats, the arrival of the first seabirds, a new piece of earth, assembled from the mantle up, in real time. The process that created Surtsey is the same process that appears to be underway at the central Bismarck Sea right now. Theory grounded in the confirmed presence of pumice rafts and the cone formation assessment from Steve Saunders. The conditions match: sustained eruption, material accumulating, cone growing upward toward the surface. Whether the Bismarck Sea site reaches the surface depends on variables that cannot be measured right now. The volume of material remaining in the magma chamber, the rate at which the eruption is depositing material versus losing it to ocean currents, the depth of the starting point. At 1,600 feet, the cone needs to gain 1,600 feet of height before breaking the surface. At 4,000 feet, it needs more than twice that. Other historical precedents show the range of outcomes. In 2013, a submarine eruption off the coast of Japan produced a new island called Nishinoshima in a matter of weeks. The island grew rapidly, eventually merging with a neighboring islet, and has continued to expand through subsequent eruptive phases. It is still above water today. In 2015, an eruption near Tonga produced a new island. That island eroded within months. because the material it was built from was loose volcanic debris that wave action quickly dismantled before the lava flows could solidify a stable base. The durability of a new volcanic island depends on what it is made of. Loose ash and pumice erode fast, solid lava flows harden into rock and resist wave action. The eruption style determines the composition. Explosive eruptions produce loose material. Effusive eruptions, where lava flows rather than explodes, produce solid rock. The central Bismarck Sea eruption appears to be predominantly explosive based on eyewitness accounts and acoustic data. That suggests the material forming the growing cone is loose. If a new island forms, it may face the same erosion challenge as the Tongan example. Whether the eruption sustains long enough to find out is the question nobody can answer from the surface. That is the honest answer to how long this eruption will last. Scientists cannot open the seafloor and measure how much magma remains in the chamber below. They cannot calculate a precise end date. What they can do is look at comparable events and describe the range of what typically happens. Submarine eruptions driven by the kind of tectonic setting present in the Bismarck Sea fall into several behavioral categories. Some eruptive phases are brief and intense. The chamber empties quickly through high-output explosive activity, pressure drops, and the eruption stops within weeks. The aftermath is a new seafloor structure, a changed water chemistry, and quiet. Some eruptive phases pulse. They produce intense activity for days, then quiet for days, then intensify again. This cycling behavior reflects a magma chamber that is being replenished from below at roughly the rate it is expelling material above. The chamber never fully empties, the eruption never fully stops, it oscillates. These events can last months or years. Some eruptive phases are prolonged and steady, a moderate output sustained over a long period, building structure slowly without the dramatic explosive peaks, but also without stopping. Surtsey ran for 3.5 years at this kind of sustained pace. The central Bismarck Sea eruption is young. It has been active for approximately 2 weeks at the time of the most recent reports. The behavior observed so far, explosive episodes, ash plumes, seismic swarm activity, is consistent with the early phase of a chamber-driven eruption, where pressure is still high and magma supply is strong. The seismic swarm behavior is the key indicator scientists are watching. Eruptions that are beginning to wind down typically show a decrease in the frequency and magnitude of associated earthquakes as the magma pressure in the chamber drops. Eruptions that are being fed by continued magma supply from below maintain or increase their seismic activity. The current data from the Bismarck Sea site shows that the seismic swarm remains active, confirmed. A sustained seismic swarm with no sign of decreasing activity suggests the eruption is not in its closing phase. The Rabaul Volcano Observatory confirmed that maritime exclusion zones will remain in place until the earthquake swarm completely subsides. That phrasing is significant. Completely subsides. Authorities are not planning for a short event. For the fishermen waiting to return to their grounds. For the scientists waiting to deploy research vessels. For the analysts watching the seismic feeds, the question of duration is not academic. An eruption that runs for months builds a much larger seafloor structure than one that ends in weeks. A larger structure changes the stability calculations. A longer eruption expands the ecological disruption zone. The variables compound as time extends. The volcano is running on its own timeline. Scientists are watching for the signals that tell them which direction that timeline is heading. Those signals exist, and knowing what to look for turns out to require understanding what underground escalation actually looks like before it reaches the surface. Scientists monitoring an active submarine eruption are not just watching what is happening now, they are watching for what comes next. The signals that indicate a major escalation fall into several categories. Each one, alone, is a data point. Several arriving at the same time form a pattern that demands immediate response. The first signal is a sudden increase in earthquake magnitude at the eruption site. Moderate seismic swarms throughout an eruption are normal background activity. A sudden jump to larger magnitude earthquakes, particularly in the range of magnitude 6 and above, indicates that a significant fault movement is occurring adjacent to the volcanic system. Large fault movements can destabilize the structure forming on the seafloor, crack open new pathways for magma, or trigger the kind of rapid structural failure that produces large wave events. The second signal is harmonic tremor. Volcanoes under active magma movement produce a specific seismic signal called harmonic tremor. It sounds on a seismometer like a sustained hum rather than the sharp spikes of discrete earthquakes. A strong harmonic tremor signal indicates that magma is moving rapidly through conduits in large volume. Scientists have confirmed this as a precursor to major eruptive escalations at multiple volcano sites globally. The Kilauea eruptions in Hawaii have provided extensive documentation of this signal, preceding major lava output increases. The third signal is a rapid increase in the surface area of discolored water. Satellite imagery showing the discolored zone expanding quickly indicates that the volume of material reaching the surface is growing. A small eruption discolors a limited area. A major escalation spreads that zone across miles of ocean in a short time. The fourth signal is the ash plume height. A plume reaching 9,000 feet above sea level is significant. A plume that suddenly doubles or triples in height indicates a dramatic increase in explosive energy. Aircraft routing in the region is directly affected by large ash columns, and a major height increase would trigger aviation alerts across the Western Pacific flight corridors. The fifth signal is the one scientists most want to avoid seeing: a sudden disappearance of all surface activity. When a volcanic system goes completely quiet after sustained eruption, it sometimes means the eruption has ended, and sometimes it means a structural failure has occurred below. The vent has collapsed or shifted, and the system is reorganizing under pressure for a more violent release. The Rabaul Volcano Observatory is tracking all of these signals continuously with the instruments available. The Pacific Tsunami Warning Center is monitoring the seismic and buoy network for wave signatures. Nothing in the current data has crossed into the escalation warning territory, confirmed as of the most recent reports. The eruption is active, sustained, and monitored. The system is watching, and below the surface, the ecological consequences of what has already happened are playing out across a web of life that has no warning system at all. Tuna do not stay where conditions turn against them. The Western Pacific tuna fishery is one of the most productive on Earth. The Bismarck Sea and the surrounding ocean provide feeding grounds and migration corridors for several major tuna species, including skipjack, yellowfin, and bigeye. These fish are migratory. They follow water temperature gradients, prey distribution, and oxygen levels across thousands of miles of ocean. When any of those conditions shift significantly in a given area, the fish move. The eruption has altered the conditions in the central Bismarck Sea in several measurable ways. Confirmed, water temperature in the area above the vent is elevated. Dissolved volcanic gases have altered the local ocean chemistry. Dead fish from the immediate eruption zone have disrupted the local food web at small scales. The ash fallout from the surface plume has deposited material across a zone extending outward from the eruption point. The short-term effect on tuna in the immediate area is the fish kill that appeared the morning after the main eruption. Those were almost certainly a combination of reef and midwater species caught close to the vent when it opened, not the large open ocean tuna populations that commercial fishermen target. The medium-term effect on commercial tuna is subtler and more consequential. Tuna locate food by following the convergence zones where different water masses meet, where prey concentrations build up, and where temperature gradients create productive feeding conditions. A submarine eruption introduces a new large thermal anomaly into the area. The warm water plume rising from the vent alters the temperature structure of the water column above it. Prey species respond to that change by redistributing. Tuna follow their prey. The eruption effectively rewrites the local map that tuna and fishermen both depend on. How long that rewrite persists depends on how long the eruption continues and how quickly the ocean chemistry normalizes once it stops. In areas with confirmed prior submarine eruption events, recovery of fish populations to their pre-eruption distribution patterns took months to years, depending on the scale and duration of the eruption. The long-term effect on the Bismarck Sea tuna population remains completely undocumented. Unknown. The eruption is ongoing. No scientific survey of the ecological impact has been possible within the exclusion zone. For fishing communities in Papua New Guinea and surrounding islands, this is an economic and food security issue running in parallel with the geological event. These communities operate on tight margins. A disruption of months to their primary fishing grounds creates real hardship that persists beyond any news cycle covering the volcano itself. The volcano's geological timeline and the fishing community's economic timeline are completely mismatched. The geology will resolve when it resolves. The families who depend on those waters are facing a gap that has no predictable end date. The ocean chemistry that is shifting around the vent is not only disrupting what lives there, it is also doing something to the water itself that scientists find important for an entirely different reason. The ocean above the vent is being chemically altered in real time. This is confirmed and ongoing. The gases escaping from the eruption are not just rising into the air. A significant portion dissolves directly into the surrounding ocean water as the rising column passes through it. The result is a zone of chemically modified ocean water spreading outward from the vent with every passing day. The primary chemical agent is sulfur dioxide. When sulfur dioxide dissolves in water, it forms sulfurous acid. That acid lowers the pH of the surrounding water, making it more acidic. In the immediate vicinity of the vent, the pH drop is dramatic and happens fast. Waters close to active submarine vents have been measured at pH levels far below the normal ocean range. Normal ocean water has a pH of around 8.1. Highly acidified water near an active vent can drop below 6, 100 times more acidic than normal seawater. This acidification is immediately lethal to the organisms in the zone, confirmed across multiple documented submarine eruption events. Shell-forming organisms dissolve. Coral structures are chemically attacked. Fish experience physiological stress from breathing acidic water through their gills. The organisms least equipped to handle rapid pH change are also the ones that form the base of the food web: plankton, small crustaceans, juvenile fish. Carbon dioxide is the second major dissolved gas. The ocean naturally absorbs carbon dioxide from the atmosphere, and this process has been increasing as atmospheric carbon dioxide levels rise. A submarine eruption adds a local burst of carbon dioxide directly into the water column. At depth, under pressure, carbon dioxide dissolves readily. As the gas-laden water rises and pressure drops, the carbon dioxide comes out of solution and escapes into the air. This cycling creates a zone of elevated dissolved carbon dioxide in the water column between the vent and the surface. Elevated dissolved carbon dioxide causes its own acidification through a different chemical pathway than sulfur dioxide. The two mechanisms together produce a compounded acidification effect in the water directly above the eruption. Hydrogen sulfide adds a third dimension. At low concentrations, hydrogen sulfide is toxic to marine organisms. It inhibits cellular respiration in fish and invertebrates. At the concentrations present near an active vent, it contributes directly to the kind of mass mortality observed in the fish kill the morning after the eruption. The modified water zone is not static. Ocean currents carry it. The chemistry spreads outward from the vent as the eruption continues. Monitoring its extent would require water sampling from vessels in the area, which the exclusion zone prevents. Scientists are estimating the spread based on models calibrated to the eruption's observed output, not direct measurement. The chemistry will normalize after the eruption stops. The ocean has a buffering capacity that slowly returns disturbed water to its normal pH. The timescale for that recovery varies with the severity and duration of the disruption. The longer this eruption runs, the larger the chemically altered zone becomes. And the tools that could eventually document and understand that zone require getting a ship into the water above a structure that is still building itself upward in the dark. The seafloor does not reveal itself easily. When the exclusion zone around the central Bismarck Sea eruption is lifted and the seismic swarm has subsided enough to make approach safe, scientists will begin planning what comes next. The question waiting for them is simple and enormous at the same time. What does the seafloor look like now? The primary tool for answering that question from the surface is multi-beam sonar. A research vessel equipped with multi-beam sonar emits sound waves downward in a wide fan pattern as it travels across the surface. The sound waves travel down to the seafloor, bounce back, and are detected by receivers on the hull. The time it takes for each echo to return, combined with the angle it came from, gives the computer a precise depth measurement for each point on the seafloor below the ship. By traveling a series of parallel tracks over an area, the ship builds up a complete three-dimensional picture of the seafloor topography beneath it. The resolution of a modern multi-beam sonar survey is fine enough to reveal features a few feet across, even at depths of thousands of feet. A survey covering the central Bismarck Sea eruption site would reveal the size and shape of the cone that formed during this eruptive phase, the new topography of the fissure ridge, the extent of the debris field around the vent, and the overall change in seafloor height. Comparing that new survey to the older, lower-resolution maps that existed before May 8th would show scientists precisely how much the seafloor has changed, how tall the new structure is, how much material was deposited. For closer examination, research vessels can deploy remotely operated vehicles. These are robotic submarines connected to the ship above by a tether carrying power and data signals. They carry cameras, sonar, water sampling equipment, and robotic arms capable of collecting physical samples. A remotely operated vehicle can descend to the seafloor, navigate directly to the vent area, and return video of the actual surface in real time. That video would be extraordinary. Nobody has seen the current state of the central Bismarck Sea seafloor. The cone forming there has never been photographed. The vent structure, the lava flows, if any exist, the distribution of fresh volcanic material across the surrounding seafloor, all of it remains invisible to human eyes. Autonomous underwater vehicles add another capability. These are untethered robotic submarines that can be programmed to follow survey patterns independently, covering large areas without requiring the research vessel to move directly above every point. They are deployed, complete their survey, and are recovered to deliver their stored data. Water sampling at depth will tell scientists about the chemistry of the water column directly above the vent, the temperature gradient, the gas concentrations at various depths, and the extent of the biological impact zone. The confirmed plan from Papua New Guinea authorities is that future marine expeditions will map the altered seafloor once the waters clear and the immediate danger passes. The science is waiting for the geology to allow it. The same question applies on a far larger scale to the rest of the unmapped ocean floor. The warning system worked in one specific way and failed in another. The seismic network detected the May 8th earthquake immediately, confirmed. Magnitude readings were produced within minutes of the event. The Mineral Resources Authority in Papua New Guinea had data quickly and began assessing it. The Pacific Tsunami Warning Center was monitoring. In terms of the earthquake itself, the detection was fast and the threat assessment was appropriately calibrated. The volcanic eruption that followed required eyewitnesses to confirm. That gap reveals something important about the current state of Pacific early warning infrastructure. The system is built primarily around earthquake detection. The global seismic network is dense enough and sensitive enough to detect and locate earthquakes of significant magnitude almost anywhere on Earth within minutes. This capability is mature, reliable, and well-funded. Submarine volcanic eruption monitoring is a different problem. An underwater eruption that begins quietly, without a major preceding earthquake, could develop for hours or days before producing any surface signal. A vent opening slowly, gas venting gradually, a plume beginning to form below the surface. None of that necessarily produces a seismic signal large enough to flag automatically. The first detection might again be a fisherman who happened to be in the area. The tools that could provide better early warning for submarine eruptions exist but are not deployed at scale across the Pacific. Hydroacoustic monitoring, listening to the ocean through underwater microphone networks, can detect submarine eruptions at great distances. The existing network, originally built for other purposes, covers parts of the Pacific, but has significant gaps. The central Bismarck Sea site is not in the densely monitored zone of that network. Ocean bottom seismometers, devices placed directly on the seafloor, would provide far more sensitive local earthquake detection than land-based sensors. For a submarine volcanic system, a cluster of ocean bottom seismometers positioned around the known Fisher Ridge would have detected the buildup of seismic activity beneath the vent well before May 8th, potentially providing days of advance notice rather than the hours the surface community got. These instruments are expensive, difficult to deploy and retrieve, and require ongoing maintenance from research vessels. The number deployed across the Pacific is a fraction of what a comprehensive early warning network would require. The Bismarck Sea eruption exposed the gap between the submarine volcanic hazard that exists across the Pacific Basin and the monitoring infrastructure currently in place to detect it. Confirmed by the events, eyewitness reports were a primary data source for days. A more dangerous event, one developing faster with less opportunity for human observers to provide warning, could outrun the current system entirely. The technology to close this gap exists. Deploying it at the scale the Pacific requires is a question of resources and political will that has not yet been fully answered. The central Bismarck Sea volcano spent 54 years unmonitored, and it was one of the ones scientists knew about. The Smithsonian Institution's Global Volcanism Program maintains the most comprehensive catalogue of Earth's volcanoes. The catalogue lists roughly 1,500 volcanoes that have been active in the last 10,000 years, meaning volcanoes with a confirmed eruption history within the geological recent past. Of those, approximately 500 are submarine or partially submarine structures. Those 500 are the known ones, the ones that erupted at some point and produced a signal that humans detected and recorded. They represent a fraction of the actual number. Scientists estimate that the total number of volcanic features on the ocean floor exceeds 1 million. The vast majority of those have never been observed, never been surveyed in detail, and have no recorded eruption history. They exist as topographic features on the few seafloor maps that cover their locations, logged as seamounts or ridges without any assessment of their volcanic status, activity history, or current state. Some of those structures are ancient and geologically dead. The magma source that fed them was cut off millions of years ago when the plate carrying them moved away from the hotspot or subduction zone below. They will never erupt again. Others are dormant exactly the way the central Bismarck Sea volcano was dormant. Chambers filled with magma. Fault lines locked under pressure, waiting for a trigger. Some of them may have eruption return intervals measured in centuries or millennia. Some may be approaching the end of a long dormant period right now, with no monitoring system watching and no catalogue entry flagging them as a concern. The central Bismarck Sea volcano's 54 years of silence is a short dormancy by geological standards. Volcanoes can sleep for thousands of years and reawaken. The catalogue of known submarine volcanoes with eruption histories tells scientists something about a small portion of the structures on the ocean floor. The portion of the total that the catalogue represents is genuinely unknown. The ocean floor mapping effort, if completed at high resolution globally, would identify the full population of volcanic structures on the seafloor. It would allow geologists to assess which structures have the morphology of recently active systems, which show signs of fresh lava flows indicating recent eruption, and which sit in tectonic settings that make future activity likely. That mapping effort is underway but nowhere near complete. Various international programs, including efforts using autonomous underwater vehicles and satellite-derived depth models, have been extending coverage. The rate of progress is slow relative to the scale of the task. The central Bismarck Sea eruption is a reminder that the ocean floor is not a static background. It is an active geological surface, largely unseen, where events are happening that the systems humans have built to monitor Earth's hazards are only partially equipped to detect. What the eruption ultimately becomes, island, seamount, or a quiet return to the deep, will shape how scientists think about this site and the hundreds like it they have not yet found. The future of the central Bismarck Sea volcano has several possible shapes. None of them are certain. All of them are being considered. The first scenario is the one scientists consider most probable, given the current data. The eruption continues for weeks to months at a sustained output level, building up a significant seafloor structure, then gradually subsides as the magma chamber pressure drops. The result is a new seamount on the floor of the Bismarck Sea, a large underwater mountain that does not break the surface but permanently alters the local seafloor topography. The seismic swarm winds down. The exclusion zone lifts. Research vessels arrive and map what was built. Marine expeditions document the ecological recovery. The event joins the scientific record as a significant but ultimately contained submarine eruption in a geologically active region. The second scenario involves the cone breaking the surface. If the magma supply sustains the eruption long enough, and the output volume remains high, the growing structure eventually rises above sea level. A new island appears. Scientists race to document it. The island is composed largely of loose volcanic material and faces immediate wave erosion. Its survival as a permanent landmass depends on whether lava flows harden a stable base before erosion dismantles the loose debris. If the lava wins, a new island is added to the map of Papua New Guinea. If erosion wins, it disappears within months or years. Theory based on comparable events, but physically plausible given the confirmed cone formation. The third scenario is the one the official scientific bodies consider low probability, but have not ruled out. A structural failure. The growing cone, built rapidly from loose material on an unstable microplate boundary, fails. A section of the new structure collapses into the ocean, displacing water rapidly. The collapse generates a localized tsunami. The wave's impact depends on the volume of material and the direction of the collapse relative to nearby coastlines. The Ritter Island precedent from 1888, 124 miles south, sits in the historical record as proof that this mechanism operates in this specific region. Low probability. The fourth scenario is the one independent researchers raise and official bodies reject: an extended, high-output eruption combined with ongoing seismic swarm activity feeds stress into the fault systems adjacent to the central Bismarck Sea site. A secondary fault rupture of larger magnitude follows, either triggered by the stress redistribution from the eruption or by the natural progression of the regional tectonic cycle. That secondary event, on a major fault in the Bismarck Sea zone, produces a seismic and potentially tsunami sequence that exceeds the current eruption in impact. Theory without confirmed supporting data, maintained as a scenario by researchers who believe the tectonic connections across the arc are tighter than official models acknowledge. The volcano underneath the Bismarck Sea does not know about any of these scenarios. It is following physics, pressure, heat, chemistry, and the mechanics of fluid moving through fractured rock toward the surface. Kennedy Massis went looking for tuna, 62 miles from shore, and found the opening of a geological event that scientists will study for decades. The smell hit him first, then the sound, then the sight of ocean behaving in a way that ocean is not supposed to behave. Below him, something that had been asleep for 54 years was waking up. It is still awake,